Hi Logic students, this is a video on proofs. In previous videos we talked about symbolization, but you know that the exercises in the textbook ask you not just to symbolize these arguments, but also to construct a proof of their validity. So what is a proof? We'll get to this in a second, but a proof is basically a way to show that an argument is valid, and it consists in a series of steps where each step is properly justified, and at the end of this process the final step is the conclusion of the argument. So with a proof you're kind of teasing the conclusion out of the argument. So you'll see how it works in a second, but here's one of the examples that we did in a previous video. This argument, if Darnell is lost then Frank will find him, Darnell is lost and Edward is just arriving, so Frank will find Darnell. So we symbolize this argument as if Darnell is lost, then Frank will find him. Darnell is lost and Edward is just arriving. And the conclusion was Frank will find Darnell. So the symbolization allows you to see the structure of the argument really well. So now we can talk in terms of D and F and sort of an E and forget about what the argument was originally about. It doesn't matter who these people are and so forth. The argument is valid on account of its structure, of how it's put together. It's not valid because it talks about Frank, Darnell, and Edward. So what is a proof? As I was saying earlier, if this argument is valid, F, the conclusion, follows necessarily from these two premises. It follows from them. And you can see that F is here. So a proof is a tool for showing that you can go from these two premises to the conclusion in a series of steps, where each step is an application of one of those rules of inferences and equivalencies and postulates that the textbook lists for us. And there is a handout that includes all of those, a handout I distributed. So you can see that some are equivalencies, so there are ways to rewrite certain propositions. Others are postulates, so basic truths, and others, there's more equivalencies, and others are what you would call rules of inference, so ways to derive a conclusion from premises. Now, how do you know how you're supposed to proceed here, and which rules or equivalencies you need to use? Well, it depends on what you have, and so you have to think in terms of the premises that you have and what rules or equivalencies you can apply to them. So you'll see how it works in a minute, but first you have to set up the proof. And setting up the proof means that you make some numbered lines. Each line has to have a number. And the first thing you do is you enter the premises on numbered lines. So you go, this is the proof. The first line is if D, then F. And you say that you entered it as a premise. So each line must have a justification. You must show that you have a reason, so to speak, to enter that line. The second line will be the second premise. D and E. And this too is justified as a premise. Okay, you don't enter the conclusion, of course, because your job is to do a series of transformations so that at the end the conclusion pops out in the proof. So the conclusion is kind of on the side. You can write it on the side as a reminder, but you cannot enter it in the proof just yet. Okay, so now your job is to take more steps so that in the end you're able to enter a line that only contains f in it, because that will accomplish the proof. It will show that f follows from these premises. So now what do you do? What can you do with these premises? So what you have to do is remind yourselves of those equivalencies and rules of inference and see if there are any that are applicable to these premises. And for example, this premise, D and E, is a conjunction. It's two statements next to each other and joined by and. Is there something you can do with conjunctions? Well, you can go to the list and you can see that, well, here's an interesting postulate. You know that whenever you have two statements that are joined as a conjunction, this is written P and Q with lowercase p and lowercase q. That means you have to take these lowercase p's and q's as meaning any statement whatsoever. So if you have any statement whatsoever, call that P. And then the AND sign, and then any statement whatsoever, call that Q. You can detach the P on its own. If you think about it, that makes an enormous amount of sense. If you have a sandwich with ham and cheese, it certainly follows that you have a sandwich with ham. If you have them both, then certainly you have one of them. So P and Q entail P. So back to our proof, D and E entail D. Of course, you can detach D on its own. So on line 3, you can enter D. And this will be justified by that postulate, which is called simplification. You can simplify a conjunction. So the justification for line 3 will be line 2, because I took D and E, which was on line 2, and the rule that I use is simplification. I think that's abbreviated as SI. Some textbooks abbreviate that as simp or simplification, but this textbook uses SI. Okay, so now I have a third line. Well, let's see if I can do something here. There's something interesting that is probably jumping out to you. I have if D then F on line 1, and I have D alone on line 3. So there's kind of a match here between this conditional, the antecedent of the conditional is D, and then I have D on its own. So let's see if I can do something with this. You know, conditionals are really helpful for drawing inferences. So let's go back to the list and let's see if there are any rules that involve conditionals. Look at this one, modus ponens. It tells you that if you have a conditional, if P then Q, so again, any formula whatsoever followed by a horseshoe, followed by any formula whatsoever. So this could be if A then B, if Z then W, or even things that are more complicated. But anyway, if you have a conditional, and then you have the antecedent of that conditional on its own, you can derive the consequent of that conditional. If P then Q and P entail Q. Again, this makes a huge amount of sense. If you know that, let's say that you know that if it rains, then Bob always brings his umbrella. And then you look out the window and you see that it's raining. Obviously, you conclude that Bob will be bringing his umbrella. So the conditional says that P is sufficient for Q. So if P occurs, Q occurs as well. So let's go back to our proof. We can enter a fourth line. So remember, each line has to be numbered. And on this line, I can put together 1 and 3, and by modus ponens, if P then Q, P therefore Q. In my case, if D then F, D therefore F. So I can enter F, and I'll be justifying it by lines 1, 3, and MP, or modus ponens. Okay, and now, well, I'm done, because as you can see, just by unpacking these premises a little bit, I was able to produce F on its own, which is the conclusion of this argument. So the proof has been accomplished. I was able to show that the conclusion F follows from premises 1 and 2 by a sequence of steps where each step is properly justified. It's applied to a previous line or previous lines, and it's justified by one of the equivalencies or rules that are just like the basic tools of logic. I hope this video is useful to you. Let me know if you have any questions. Thank you very much.